So this is again a new class on the same module of magnetic ceramics, and we were at the end of discussing the ferromagnetism. And in the ferromagnetism, one of the important concept is to explain the ferromagnetism and to explain the Curie transition or Curie-Weiss transition. What is proposed is molecular field theory. Now, this molecular field theory was proposed by Weiss in 1907, and this was essentially to explain that why in ferromagnets the atomic spins align in one direction, because the picture, the microscopic picture of moments is like this in ferromagnetic materials. You have spontaneous alignment of magnetic dipoles. Now, this gives rise to spontaneous magnetization, that too large. So, the question was, why does it happen? Now, the basis for this came from Weiss in 1907, who proposed that this ordering of spins in one direction is because of some neighborhood effect, and this neighborhood effect is nothing but having some internal field inside the material because of presence of neighbors around each atom, and this internal field is something which helps in keeping these spins aligned in one direction. Although this concept is proven wrong little later, because when we go into details, we find that the field requirement to satisfy this condition is extremely large. You need to require fields of the order of kilotesla, which is extremely large field, and which cannot be generated even by the best of the machines. So, but this sort of laid the foundation of finding the fundamental aspects of this magnetic ordering in ferromagnets. So, what he postulated in 1907, something called as internal field, and this internal field is similar to what we saw in electrics in module 4 as an internal field which helps in which acts on top of the applied field, and this is again because of the presence of surrounding ions on the particular atom. So this internal field modifies the total expression for the field. So now, if you write this internal field expression, let us say this is Hi, and this Hi is now modified by, this is applied field H, and then you have what is called as Hw, which is nothing but Weiss field or molecular field, some sort of molecular field because of presence of ions. Now, this molecular field was later conceived by Weiss as gamma m, where gamma is nothing but a Weiss constant or a molecular constant. So this gamma was molecular constant, and as a result, what you have now is, so for a ferromagnetic material, now susceptibility is m by h, and if you replace this h by the modified expression for h, so it becomes m by h divided by h plus gamma m, and and what was this equal to? From the Curie's behavior, this was equal to c by t. So what you get after modifying this expression is m by h to be equal to c divided by t minus gamma c. Now this gamma c turns out to be equal to what is called as Curie temperature. Now this Curie temperature is same as transition temperature for most practical purposes, but when you look at it microscopically in the vicinity of this transition temperature, they are a little different. So as a result, this particular expression is called as Curie-Weiss law or Curie-Weiss behavior. So what you have in the plot of magnetism and magnetization and susceptibility now is, when you plot magnetization first as a function of temperature. So magnetization starts from Ms, which is a saturation magnetization, and then it drops near the temperature, which is, let us say, the transition temperature Tc, the Curie temperature, the most the temperature which we conceive best. But what happens is that there is a divergence near the Tc and it dies off slowly. So it comes up to this point and then it dies off slowly and it goes to temperature theta, and this is what this is. So now you can understand what is theta and what is Tc, and this is best reflected in the susceptibility part. So what you have in susceptibility part is essentially, so this is your 1 over chi term, and what you have is a divergence or the susceptibility which leads to slow move towards Tc. So what you have is, so this region will of course be paramagnetic and this would be of course the ferromagnetic. So this little discrepancy in Tc and theta is because of Curie-Weiss behavior, and although for most practical purposes in all the books you will find that this Ms curve drops right at Tc itself. So this is one of the differences from the Curie behavior as we saw earlier for paramagnets. So what you have here is, you call theta as a temperature for paramagnetic transition temperature, and then Tc can be called as a ferromagnetic transition temperature, and in between the lines remain little fuzzy. So these are the two lines which demarcate the difference between ferromagnetic and paramagnetic behavior. Now if you can sort of roughly work out what is the value of this applied field, and before we do that, just to remember that theta is greater than Tc in most of the cases, and what this means is that the molecular field is acting in the direction of applied spins. So this sort of helps, because this is what you should expect for ferromagnets, because the moments are aligned parallel to each other. And so now if you calculate, you can roughly estimate the direction of this applied field, and this applied field, let us say near the transition temperature, where the thermal energy is Tc, and the moment magnetization which is because of this molecular field is mu b hw, and if you now calculate this hw, which is kTc divided by mu b, this works out to be, for most ferromagnets with transition temperatures which are reasonably well above room temperature, this is of the order of kilotesla, and this is a very large field. You cannot achieve even this on very good machines. So as a result, there was something wrong with this concept of molecular field. So later what emerged was, what helps in aligning these atomic spins is the concept of exchange energy. And this exchange energy is because of exchange interaction between these spins, which is a purely quantum mechanical concept. And what this says is that you have exchange energy which is given by this Hamiltonian expression, Heisenberg Hamiltonian expression, which says that Hex, the Hamiltonian, is equal to minus of sigma ij, and then you have j multiplied by Si Sj. So you calculate the overall energy for all the spins multiplied by a factor which is called as a J exchange, or exchange interaction constant, or exchange integral. A lot of times you can approximate both of them, and which depends upon the interaction between the electron proton, and so on and so forth. We will not go into details of that, and you have to take the wave functions into account, but nevertheless it depends upon the atomic structure and intra-atomic interactions, and the sign of this Jx determines what kind of ordering are you going to have. So a positive value will mean that the energy will be minimum, and this positive value means that you have spins aligned in the same direction, and this gives rise to what is called as a ferromagnetic interaction. And when you look at J exchange, which is negative, and this negative means that energy is essentially SiSJ as anti-parallel. So as a result, this is the expression. So this is your another kind of ordering, which is called as antiferromagnetic ordering, which we see in the next few minutes. So this exchange energy is essentially the driving force behind this ferromagnetic interaction. Unfortunately, we cannot go into details of exchange energy because it's a little bit more complicated than what you are required to understand in this course. However, if you are interested to know about exchange energy, there are plenty of books available, such as you can read, for example, R.E. Hemmel, Electronic and Magnetic Properties of Material. They have reasonably okay treatise on the exchange interaction, and you can also read Hench and West, Electroceramics. They have a section on the description of this exchange energy. So essentially, this exchange energy is the energy which is responsible for this ferromagnetic interaction in the materials. And if you plot this, for instance, this J as a function of atomic parameters, which is let's say R AT by RD, which is essentially the atomic radius divided by the radius of the 3D orbital for 3D elements. And if you plot J, this is around 0, then you see J goes something like this. And here, somewhere here you find manganese, somewhere here you find chromium. So this is the negative value of J, which describes antiferromagnetic ordering. So you have a spin alignment like this. But if you go here somewhere, iron, cobalt, and so on and so forth. So the ferromagnetic d elements fall in this category of J, which is positive. So so this sort of explains the reasons for ferromagnetic interaction in the materials. So what we will do is that so this sort of finishes the discussion on ferromagnetic material. So what basically ferromagnets are? Ferromagnets are the materials which show spontaneous magnetization. They show what is called as presence of a hysteresis loop, and this hysteresis loop is as a result of spontaneous alignment of magnetic dipoles, but also the shape of the loop and the values of coercive field, etc., depends upon how easily or how difficult how easy or how difficult the domain movement is. And this domain concept is again similar to ferroelectric materials, which is nothing but a region of uniform magnetization, a uniform magnetic alignment, and again, because of energy reasons, you have a multi-domain structure, and the way this domain structure changes as a function of applied field, you get a characteristic hysteresis loop. So and these ferromagnetic materials also follow what is called as a Curie-Weiss behavior, which is nothing but transition from an ordered ferromagnetic state to a disordered paramagnetic state across a transition temperature, which is called as Tc. Although if you look at it more carefully, in the vicinity of Tc, you have two temperatures, Tc and theta is slightly above Tc, but nevertheless for all practical purposes it is taken to be similar. Now what I will do now is I will just show you a couple of animations based on the domain movement in ferromagnetic materials, and then we will move on to another kind of ferromagnetic ordering in materials, which is important before we move into the discussion on magnetic ceramics, things like ferrites and garnets, etc. So so essentially I will first show you this one, which is nothing but a movie on the domain. Again, we acknowledge the support of help of doitpoms.ac.uk, who have put it on their website for free circulation. So we thank for their help. So now you have a situation like this. You start at this point in the virgin material where zero magnetization is observed, and this is the idealized domain structure where you get zero magnetic moment, and this is, let's say, the applied field direction. So you start increasing the field strength in this direction, and you can see how the domain structure changes. So what you get is this vector, which is now turned in direction of applied field. Initially it was horizontal, but this was the most conducive domain alignment, and this has grown at the expense of other domains, giving rise to domain growth in these ferroelectric materials. I will just play it again for the sake of illustration. So You can see that the unfavorably oriented domains slowly get wiped out. And another animation which I want to show you is this one. So here you can see that the field is increasing and decreasing. Just focus on the black arrow and focus on the on this view graph on the right. So you see that this increasing in the field strength. Now you have complete alignment of domains. Then slowly it goes back to this point, and then you have MR and 0 MR, and then going back into negative direction. So this cycle continues, and this essentially tells you about the domain growth in ferromagnetic materials. So what I'll do now is that I'll now discuss the next class of materials, which is or next class of magnetism, which is antiferromagnetism. Okay, so this now antiferromagnetic materials are opposite to ferromagnetic materials, in the sense that while in ferromagnetic materials the alignment of spins is in this direction. So this is what is ferromagnetism. In antiferro, what you have is opposite alignment of spins, and this is your antiferromagnetism, AFM. And this happens in this happens in crystallographic materials, like so examples of this effect could be materials like NiO, MnO, some hematite Fe2O3, BiFeO3, which is again a new class of materials, and some fluorides as well. So so you can say MF2 type of fluorides. So they all show what is called as a ferromagnetism, antiferromagnetism. So essentially what happens is that in these materials you can see that there are two kinds of ions. You have one cation, one anion. Now anion is typically diamagnetic in nature, it doesn't contribute any magnetism. So what you have is magnetization being contributed, or magnetic moments come only from the nickel. So the question that you can ask is, if the magnetic moment is coming only from one type of atom, then why is that you have an anti-parallel ordering, and how is the anti-parallel ordering happens? And essentially this gives rise to zero magnetization as well. So how does this happen? And moreover, these materials also have a temperature dependence. So they have a temperature dependence, and below a certain temperature, which is called as a Néel temperature, Tn, below which these materials remain antiferromagnetic. So below Tn, AFM, antiferromagnetism prevails, and above Tn these become paramagnet. Just like just like ferromagnet to paramagnet transition, you have an antiferromagnet to paramagnetic transition, but the temperature is not called as Curie temperature, it's called as Néel temperature. So how it happens? So for instance, we take example of nickel oxide. So you take a nickel oxide has NaCl structure. So NaCl structure is something like this. So you have, if you just look at, for instance, this is your NaCl. You have to go back to module 1 to see this, but here I will draw it for you. So you have so these are your corner atoms. Now both of the ions make FCC lattice. So typically the base lattice is made by using anions. So we make FCC lattice using anions, which is chlorine, oxygen in this case. So this is the base lattice made by oxygen atoms. Now where does the nickel atom go? Nickel atom goes to the tetrahedral sides. So these are the tetrahedral sides for nickel. And one at the body center, so right in the middle at half. So you have these all the tetrahedral sides occupied by nickel atoms. So this is nickel and this is oxygen. So this is the crystal structure. Now what happens here is, the best way to represent antiferromagnetism is to look at only the nickel ions. Now for the representation of this antiferromagnetism, what we will do is that we will draw the plan view of 110 plane. Typically we are used to drawing 100 or 001 plan view. Here we will take a representation of 110 plane. Okay, and this 110 plane, now you can draw it you can draw it pretty well yourself, but in any case I'll draw it here. What we'll have is, or maybe let's draw, for the sake of simplicity, let us draw 100 plane. So if you draw 100 plane now, so 100 plane would be, this is your I'll just draw a few rows, not all the rows. Okay, and the nickel atom goes, so this is your nickel, all right, and then you have one at this position, then of course you have at these positions, and you have of course another nickel atom sitting at the center of these faces. So this is oxygen atom, all of them. So these are all oxygen atoms, and these are all nickel atoms. Okay, now what happens here is, so this direction is your, let's say, 100 direction, and this direction would be so this is, we have taken 100, so so this would be 010 and this would be 001. Okay, now what would be this kind of plane? So if I draw a line like this along, just connecting these atoms, so this is nothing but your diagonal across the face, and this diagonal, if you take it inside, this diagonal will represent what is called as a 110 plane, 110 type of plane. Okay, so these along this direction, all the atoms are oxygen, they don't contribute to magnetism, but below, but you have the series of these 110 planes. So another plane is this, another plane is this. So remove the oxygens from there, don't count the oxygen. What you have now in these 110 planes is, in one of the planes, these in one of the planes, these nickel atoms, let us say here, are spin up, but in the other planes they are spin down. So what you have here is spin down. Since you have to maintain the stoichiometry of material, the net up spins cancel the net down spins. As a result, what you have is 0 magnetization. So you can say essentially that in NiO, oxygen no contribution, nickel, half of nickel atoms spin up, half of nickel atoms spin down, and this gives rise to M is equal to 0, and this is along 110 in the alternating 110 plane. So if you draw now like this is 1, 2, 3, 4, 5, 6. So this is 110.1, this is 110.2, this is 110.3, this is 110.4, 110.5, 110.6. So the nickel atoms here would give rise to positive, here it would be negative, it would be positive, negative, positive, negative. So essentially it's the same picture. It's the same picture. I've just turned it around by 45 degrees so that 110 planes are now parallel to our view. So now this gives rise to M is equal to 0. So essentially you can say that there are in the FCC sublattice of nickel, there are two sublattices. One sublattice has a spin orientation up, another sublattice has a spin orientation down, and this gives rise to 0 magnetization. So I hope it's clear now. So this is what is antiferromagnetism. Now these materials also have a temperature dependence, as I said. So if you plot as a function of temperature, the first thing that you plot is let's say so we plot what we call as 1 over chi versus T. Since they don't have any magnetization, it's meaningless to plot in terms of magnetization. So what you have is which increases a little bit up to transition temperature, and then it falls back again into paramagnetic regime. So what you have here is essentially a behavior like this. And this line you can extrapolate it back, and this is in Kelvin. So this is 0 Kelvin. So this is your Tn, this is your paramagnetic Curie wise behavior, and this is your and this is, so this region is antiferromagnetic region. So of course nothing is below 0 Kelvin, you can't reach a temperature below 0 Kelvin, but if you extrapolate it to the temperature axis, what you get a temperature like minus theta, which doesn't have any practical significance, although it's of some theoretical interest to theoreticians. And then on the right you have paramagnetic region. So antiferromagnetic material, if you plot 1 by chi versus temperature, it falls down to until nil temperature is reached, and then it increases again for as you increase the temperature. So of course if you plot chi, so chi would be something like this. This would be the behavior of chi. Of course the inverse behavior, it's not so it sort of increases from 0 to some value. So you would actually start at 0, very close to 0, because you don't have any magnetic moment, and then it increases to some value near Tn, and then it falls off again. So this is what is your temperature dependence of antiferromagnetic materials. Now in antiferromagnetic materials, some materials do show some magnetization, and which is essentially because of deviation from the ideal spin configuration of perfect antiparallel configuration. So the perfect so the perfect configuration is this perfect antiferromagnetism. So you can say perfectly oops, I have plotted little wrong here. So these would be spin down. So each of these have mu b magnetization, some mu b. So let's say this is plus, this is plus, this is plus, another thing become minus, minus, minus. So all of them cancel each other. So perfectly anti-parallel configuration. And this is what is perfect antiferromagnnetism. In some materials what happens is that you can have little deviation. So this for instance may go a little bit like this. This for instance may be a little bit like this. Similarly here this may be like this, and so on and so forth. And this configuration is called as canting. So this canting is little bit deviation from the perfect antiparallel configuration, and this gives rise to a small non-zero magnetization. And these are called, and materials which show this are called as canted antiferromagnets. So this is little deviation from perfect antiferromagnetism. So I will not go into details of any of this, but it's just to explain some deviation from ideality. Next type of magnetism in this class is called as ferrimagnetism. Now ferrimagnetism is similar to antiferromagnetism. It's just that so in antiferromagnetism what you saw was you have one spin like this, another equal and opposite like this, another equal and opposite. So you have equal and opposite spins, which means they have equal and opposite magnetic moments, and they are perfectly anti-parallel to each other. So you have plus mu b, minus mu b, plus mu b, minus mu b, plus mu b, minus mu b. Now in antiferromagnetism what happens is this, so if this was, let us say, x mu b plus x mu b, let me just rub it. So let us say this is x mu b what you have in the other direction is not exactly equal. So what you have in the other direction is rather something like this. So the length of the vector shows the length of the arrow shows the magnitude. So this is, let's say, y mu b minus y mu b minus y mu b minus y mu b. And here for the sake of illustration x is greater than y. So now when you calculate the overall magnetization, of course overall magnetization would be number of atoms multiplied by x minus y mu b, and this is not, as long as x is bigger than y, this is not 0. So this would be the net magnetic moment. So ferrimagnetic materials are those materials which have anti-parallel alignment of spins, but these atomic spins are not equal in the magnitude, which means spin up in one direction have magnitude which is different from spin down in another direction. Now this results in a net magnetic moment, and this gives rise to what is called as a ferrimagnetism. And so essentially what you have here is different. So as you can see, the moment you have different kind of magnetic moments, you need to have different kind of atoms. So you have atoms which are of different types, and these two atoms are sit at two different sublattices, and they give rise to what is called as what results in a net magnetization. So example of this kind of behavior are materials like ferrites. So these are all ferromagnetic ceramics. So like NiFe2O4, CO Fe2O4, Fe3O4, Cu Fe2O4, and so on and so forth. Many of these ferrites have magnetism which is finite. And so on top of ferrites you have some other materials as well. So these are all called as actually they are called as spinel ferrites. So I just add a word spinel ferrites. Then you can also have hexagonal ferrites in this category, such as barium ferrite BaFe12O19. You can have garnets Y3Fe5O12 example. So you can see that most of these have ions which are magnetic in nature, and they have ions sitting on different sublattices, and they contribute differently to the total magnetic moment. It's not necessary that you have two different magnetic ions. Sometimes only one magnetic ion does the job, but it's a distribution of these ions on two different sublattices which is important. That we will see in detail when we discuss ferrites. So at the moment I'll not discuss it too much. So I'll just draw a picture. So you have basically three kinds of magnetic orderings. So you have ferromagnetic ordering, which is like this. So this is your ferromagnetic ordering. Anti-ferromagnetic ordering is this kind of ordering. So this is anti-ferromagnetic ordering, and I'll just use a different color here. So this is your anti-ferromagnetic ordering. So you can say that M is much greater than 0 at H is equal to 0, M is equal to 0 when H is equal to 0, and then you have second kind of ordering, which is ferrimagnetic ordering. So basically unequal spin moments, and what you have here is then ferrimagnet. So M is not equal to 0 when H is equal to 0. So this is the three different type of magnetic orderings that you come across in variety of magnetic materials, and this is the class which is typically magnetic ceramics. Typically, although antiferromagnets are magnetic ceramics as well, but they are of little use because of zero magnetization. So as a result, you don't really technologically they are very poorly they are not studied that well by scientists. So ferrimagnets also follow a similar Curie transition just like ferromagnets. So when you draw a transition magnetization versus temperature, so magnetization goes like this near Tc, and if you plot susceptibility, the susceptibility 1 by chi goes like this. So this is 1 over chi. So again you might have some deviation from the behavior which is perfect, but this is how the behavior typically is for a ferrimagnet. So what I'll do now is I'll just summarize all these different kind of magnetization before we go into the next part of this lecture. So what essentially we have discussed four various kinds of magnetism. So you have diamagnetism, which is essentially due to response of electrons upon the application of electric field, and this gives rise to susceptibility which is negative and temperature independent. And then you have paramagnetism, where each atom has a net magnetic moment, but all these magnetic moments are randomly placed with respect to each other. As a result, you have chi, which is positive but small. Similarly, in case of diamagnetic, it is small typically, but it is temperature dependent. So it follows a behavior of C by T. But Another class of material is ferromagnetism, where atoms do have net magnetic moment, but these spins are also aligned in one direction at below a certain temperature called as Curie temperature, and as a result chi m is large and positive, and this also has a temperature dependence of C divided by T minus theta. So, this is the temperature dependence that you see in ferromagnets. And then you have antiferromagnets, which have chi m equal to 0, very small or very tiny, and then but positive, it could be positive because of canting, and they also have a temperature dependent behavior, and they have what you call as Néel temperature. And then you have what is called as finally ferrimagnetism, which is sort of antiferromagnetism, but different because the atomic spin magnetic moments are unequal in the magnitude. As a result, chi m is 0 and large, and this is also temperature dependent. So, these are the 5 different kinds of magnetism that we discussed, and if you plot magnetic response of these materials individually. So, for a paramagnet, so for an antiferromagnet, we will start from paramagnet. So, for paramagnet, of course, for diamagnetic is temperature independent, so we do not need to do that. So, we just plot chi inverse for the temperature for the practically useful magnetic materials. So, we have paramagnet whose susceptibility is like this, it goes. So, this is your paramagnet, and then you have antiferromagnet. Antiferromagnet is something like this. So, this is your antiferromagnetic material behavior at transition T n, and then you have ferromagnet, and ferromagnet has a response typically like this. So, this is your T c, and this is, so what you have here is essentially large susceptibilities below T c. So, that is why you do not plot it before below T c. So, this is your ferromagnet, and that is how ferrimagnet also look like. So, this is the typical comparison of ferromagnetic response. Magnetization of ferromagnets is much larger as compared to rest of these materials. So, when you plot magnetization M versus for instance H, M versus H for ferromagnets is something like this, very large. Ferri is also similar. So, this is ferromagnetic. Paramagnetic is very small linear response, and diamagnetic will go other way around. So, this is dm, diamagnetic, and antiferromagnetic would be very small, close to 0. This is AFM as a function of magnetic field. So, this is how the behavior of all these different kind of magnetic materials compares with respect to each other. So, this brings us to another topic before we go into discussion on ferrites. Is the moment you have this hysteresis loop, you also have these what is called as a magnetic losses inside the material, and these magnetic losses are not only aided by, because the domain walls require energy for their movement as a result. So, it is something, so you have domain wall growth, and the moment you have growth, you have friction inside the material, you have energy dissipation, but also these materials also tend to be conducting, and they tend to have small resistivities. As a result, you have large eddy current losses. So, magnetic losses in these materials, typically they are more important actually when these materials are used in frequency dependent applications, because in frequency dependent applications you have switching of magnetic field as a function of time, and then of course you generate you have back and forth movement of domains, and this gives rise to large dissipation of energy. So, you can have alternating just like alternating electric field, you have alternating magnetic field, which is given by H is equal to H naught exponential of I omega t, and when this alternating magnetic field is applied, you have dissipation of energy inside the material. So you have essentially two kinds of losses. One is the eddy current loss, which are dependent upon the resistivity. So you can say resistivity dependent. And then you have second kind of loss, which is you can say hysteresis loss or intrinsic losses. So these are intrinsic to a ferromagnetic material, and these are essentially because of domain wall movement, because the domain wall movement requires energy, and as a result you have some dissipation of energy. So the sum of these two losses governs how lossy a material is. So this basically the energy which is dissipated, that dissipates as heat, and this is what you don't want, especially in the AC applications. So typically what you see is that while while parameters like frequency, magnetization, coercivity, they govern the second kind of loss, the resistivity of the material governs the first kind of loss. So the total hysteresis loss, so the hysteresis, essentially we look at both of these losses individually. So hysteresis loss per so net hysteresis loss, essentially hysteresis loss is the energy loss basically per cycle multiplied by, so you have essentially this is energy loss per cycle multiplied by number of cycles, and this is given essentially, so pH is given as 2FHC Br. So Br is the magnetic remanence, Hc is the coercive field, F is the frequency of applied field. So this is your pH factor, which is due to hysteresis losses. The second loss is the eddy current loss, and this eddy current power loss are given as what is called as PE, and this is given as pi d square divided by 6 rho into F into B max, and here you can see that this is the resistivity, and as the resistivity increases, as the material gets more insulating, the power loss, eddy current due to eddy current loss decrease. So that is why in applications like transformer cores etc., where eddy currents are significantly they are very important, one must use materials with slightly higher resistivity. So total power loss P total is equal to P eddy plus P hysteresis. So this is the total power loss, and the characteristic of each of these governs in the choice of material, so that the loss can be minimized, especially in the applications where loss is a crucial parameter. Another thing that emerges by use of AC field is that, just like in dielectrics, when you used AC field expression, you got expression for dielectric susceptibility, which was complex in nature. Just similarly in these materials, when you use that kind of expression, you come up with a situation where the magnetic permeability also becomes complex in nature. So essentially you are looking at frequency dependence of mu, which is the magnetic materials permeability, and so since these materials have permanent magnetic moments and which result as a result of domain alignment, and these domains are also separated by domain wall movement. Movement of this domain wall is governed by coercivity. So typically easier the domain wall movement is, what it means is that lower the coercivity of the material is. So essentially what it means is that, so the moment you are concerned with domain wall movement, so this is your domain wall structure. So the moment you are concerned with this domain wall movement, this domain wall movement can be back and forth, so can be made faster and slower depending upon the frequency of applied field. So this domain wall movement is significantly dependent on the frequency of applied field. So you can say domain wall movement strong function of frequency of applied field, and and these materials are often used in gigahertz frequency applications. So while some materials can happen easy switching at gigahertz frequency, many other materials don't. Typically ferrites have very good gigahertz frequency response. As a result, these materials are used quite a lot in gigahertz frequency region. So essentially, just like dielectric materials, this mu is essentially a complex quantity, that is why it's mu star, and this is represented as mu prime plus I mu double prime. So you have this mu prime as a real part of permeability, and mu double prime is the imaginary part, and we will see that the ratio of these two is significant in determining the power losses in the magnetic materials, and this is of immense practical importance. So we will look at the proof of this in the next class. So what I will do is that I will now summarize the overall picture of magnetism that we have got. So overall picture that emerges is you have the magnetic moment in the material emanates from two sources, essentially two important sources. First is the orbital magnetic moment, and second is the spin magnetic moment. Now, depending upon the magnetic, depending upon what contributes to what extent in a material gives rise to type of the magnetism. And when we discuss the type of the magnetism, the first category in this case was diamagnetism. And diamagnetism is essentially about, so you have it was essentially a negative response of or the magnetization induced by the materials is negative to the applied field. As a result, they have what is called as negative susceptibility. Typically, this susceptibility is smaller in nature, but this response is inherent to all the materials. The moment you have atoms and electrons, you have diamagnetic behavior. So this is something which is intrinsic to all the materials. Secondly, we discussed paramagnetism. Paramagnetism essentially in most 3D materials emanates from spin magnetic contribution, because the orbits in 3D metals are believed to be or are thought to be quenched. So as a result, they are coupled with the lattice, they don't contribute, so they don't switch back and forth when you apply magnetic field. So as a result, the magnetic field which is essentially root S into S plus 1 mu b. So this is what, or you can include a Landau G factor as well. So this is what is the spin magnetic moment for 3D materials. If you want to go for F material, then you have to bring the orbital term into picture as well. So then you make it J plus 1 mu b. So this J includes the contribution of both spin and orbital contributions. However, in paramagnetism, you have random alignment of spins. So as a result, M is equal to 0 at a finite temperature, and this, so paramagnetism essentially does not give rise to any magnetization, but it follows a temperature dependent behavior. As a result, the susceptibility decreases as the temperature increases. Now the third magnetic ordering was ferromagnetic ordering, which is one of the most important and most studied ferromagnetic magnetic aspect of the materials, and this is because of interesting nature of alignment of ferromagnetic spins. You have completely parallel alignment of spins, and as a result you have a domain structure which gives rise to a hysteresis loop, and switching under the magnetic field of course gives rise to a hysteresis loop, and the shape of this hysteresis loop, size and shape of this hysteresis loop governs what kind of ferromagnetic material it is. And this is really a very important material aspect of magnetic materials, and this is shown by most of the many 3D elements and such as iron, nickel, cobalt, etc. And most of these materials are used as permanent magnets, memories, etc. And then we came across antiferromagnetic and ferrimagnetic materials, and this is a different kind of magnetic ordering. You have opposite alignment of spins, but the magnitude of these these two oppositely oriented spins determines whether you have an antiferromagnetic behavior or a ferrimagnetic behavior. So you can say ferrimagnetic behavior, and this typically most of these materials which show this kind of behavior, they happen to be ceramics. And this is where we will take this case of ferrimagnets, which are typically ferrites in nature, or ferrites are ferrimagnets in nature, sorry. And we will take the examples of these ferrites. You can have cubic ferrites, you can have hexagonal ferrites, you can have garnets. Most of them contain all of them contain magnetic ions, but the distribution of these magnetic ions on various cation sublattices determine what kind of magnetic response you get. So what we will do in the next class is we will complete the discussion on the frequency dependence of permeability, to look at how the losses can be explained in terms of real and imaginary part of permeability, and we will then look at the microscopic determination of magnetization in the ferrites, which are nothing but ferromagnetic ceramic, you can say ferrimagnetic ceramics. Okay, so we will close this class here, and we will take up these issues in the next class. We will have about 2 lectures to go forward before we finish this module and enter the next phase of this module. Thank you.